So, welcome back. We will start our second lecture, and this lecture will be given by Professor Florian Niedermann of Nordita. So, Professor Florian Niedermann's primary research interest is on early dark energy models, then aspects of modified gravity. So, he'll be teaching us the cosmological standard model, its tensions, and new physics.
So now you should hear me fine. Okay, great. Yeah, thank you very much. Let me first say that I'm very happy and excited to be here. I'm looking forward to that week, and I hope we can well engage in some nice physics discussions. So this lecture is going to be about, as the title says, the cosmological standard model, its tensions, and new physics. So in the beginning, let me take a little bit of time to explain what I mean by these things and what I'm going to talk about in more detail. So the cosmological standard model, in short, we typically call it the lambda CDM model, is something we are quite proud about in cosmology. And the reason is that it's a very simple model, actually. So sometimes people quote that number. It has only 6 parameters. And it allows us to describe the evolution of the universe from within a fraction of a second close to the Big Bang until today. And that's, if you think about it, a quite remarkable thing. And in particular, it allows us to get some of the observables we have in physics right. And most prominently, this is the CMB, and in Rishi's lecture, I think you will learn much more about it. And that's something quite fascinating to me. I mean, the CMB is a snapshot of the universe when it still was fairly young, only a couple of 100,000 years after the Big Bang, and we can still understand the physics that led to it, and by that really look back into the early stage of the universe, which if you think about it, is an amazing thing. And this is allowed by having this cosmological standard model. But the cosmological standard model, and that's important to state, is very different from the standard model in particle physics, because it's not a fundamental model. There are very phenomenological concepts going in it, like dark energy and dark matter, and we don't know what it is. So that's one challenge we have with the cosmological standard model. And I bet you have all seen the budget of the energy budget of the standard model. And what we know is that, well, there's something we call dark energy, and it makes up around 70% of the budget. And then there's something we call dark matter, and it makes up maybe 25% of the energy budget. And then there's ordinary matter. So ordinary matter would be everything we can attribute to something in the standard model of particle physics, and that's 5%. So that's already at this stage, we know we are lacking quite some fundamental understanding of what that model is at a more fundamental level. And this situation is ongoing now. I mean, since the cosmological standard model started out maybe 20 years ago, so as a really successful model. But now, more recently, there has been this development that there are additional phenomenological problems in the standard model of cosmology, and these typically go under the name of the cosmic tensions. And I bet you have all heard about the Hubble tension. So who has heard about the Hubble tension? Yeah, so almost everyone, I would bet. And this is I mean, a sign of the times we're in cosmology. I mean, no matter who you talk to, if you sit down with colleagues, at some point the discussion goes to the Hubble tension. And then opinions are typically very divided. Some people think it's not a real problem we should care about now. Other people are very invested in it. And at least there is always a debate about it. But these cosmic tensions are, and I will argue for that possibility, an interesting observation, because so what are they? So there are different cosmic tensions, but the most prominent one is the Hubble tension, and it's a discrepancy in the observation of the Hubble rate today. So it's the expansion rate of the universe today. And if you think about it, this is really the most basic observable you can think about in cosmology. And even that basic observable, we get contradicting measurements. And this is what we call the Hubble tension. And I will spend some time in this lecture explaining what this tension is and why people get excited about it, and what in principle can be done about it. And this will be the third part of the lecture, which then is about new physics. So the outline of the lecture is going to be relatively simple. So there is a part A, which is a recap of the lambda CDM model. So here I will talk, most of these things are probably going to be familiar with you at some level. So I will talk about the background evolution of the lambda CDM model. We will do a little bit of perturbation theory, because that's very crucial. Once you try to change the lambda CDM model, you have to make sure that existing observables are not compromised, in particular the CMB. And in order to understand the CMB, we need a little bit of perturbation theory, but luckily there is this other lecture by Rishi in parallel, and that will help a lot with that. Okay, that's the first part of the lecture. In the second part, and in the first part I will also summarize what the Hubble tension is, mostly from a theory perspective, so we can learn about how to think about it in terms of new physics. But I will also mention what is called the S8 tension, which has to do with the matter-power spectrum of the universe as another problem we have. And in part B of the lecture, I will talk about mechanisms to address the tensions. So I call it beyond lambda CDM. And in the third part of the lecture, what is important here beyond lambda CDM, here I really want to talk about mechanisms, not concrete models. So here we will talk about ideas like a dark radiation fluid. We will introduce the idea of a new phase of dark energy at early times, which is called early dark energy, without committing to a particular model. And we will also learn about scalar fields, homogeneous scalar fields, which are an important building block in cosmological model building and their evolution. So everything you learn in part B is applicable to cosmological model building in very general terms, going beyond the cosmic tensions. And only in part C, I want to talk about a concrete idea. And in part C, we are going to talk about phase transitions, cosmological phase transitions. So the plan is that today and tomorrow, it's mostly about, today is about the lambda CDM model, a recap of it. There will be quite some overlap with the previous lecture. But I think it's fine because I come from a slightly different angle. Then tomorrow we learn about the Hubble tension and the S8 tension, and well, another theoretical problem there is, which I also would call a cosmic tensions, but typically people wouldn't call it that. And then on Wednesday and Thursday, we talk about beyond lambda CDM, these concepts, and on Friday, I am going to talk about the phase transition idea. So at least that's the idea at this stage. So the tutorials are conducted by Purva, and yeah, I think what is important about the tutorials, they are somewhat complementary to the lecture. So I will mostly focus you on the theoretical concepts, but then the details are often worked out in the tutorials, or also there are more kind of data hands-on problems. And I think that Huba is the right person to teach you that, because she's also working on these things, in particular learning about well, the constraints coming from data in a rather model agnostic way, which I think is a very, very interesting approach. Yeah, I think that's all about the introduction I wanted to say. There's a lecture script, handwritten, let's call it that way, which is a somewhat extended version of what I'm going to write down. I put it for part A already in the Drive folder, so you can find it there. Part B and part C are going to follow once they are ready. Okay, very good. So let's start. So I think it makes sense to start with the basics. So as I said, there's going to be some overlap with the previous lecture, but yeah, I think it might still make sense to start slowly. So as I said, we start with the lambda CDM model, and we start with the background evolution, which means we look at a homogeneous universe. So homogeneous just means it's, well, on large scales, it looks the same everywhere. And as you know, this is described by an FRW geometry, which assumes an isotropy. So the universe looks the same in every direction, and homogeneity. And I will be a little bit more general than in the previous lecture and include the possibility of spatial curvature, just because now this lecture is more aimed at beyond lambda CDM, and so we want to also think about these simple concepts, how you can extend the lambda CDM model, and one of these concepts is spatial curvature. So so we have, yeah, let's split it in that way. We have our scale factor, and then we have a spatial slice, which I call like that. And now in the presence of, so I use spherical coordinates, and in the presence of spatial curvature, we have this correction term here. And so K times, I should probably write bigger, right? Yeah, K times R squared divided by some scale R0 squared. And this scale R0 really is the curvature scale of the spatial curvature scale of the universe. But then there's also the angular line element, which is theta squared plus sine theta squared d phi squared. And now there are three possibilities. The universe can be perfectly flat. So each spatial slice has the topology, Euclidean topology. It can be closed. Then each spatial slice has the topology of a three-sphere. Or it can be open for K being -1. And then it's a three-dimensional hyperboloid, and we would call it open. So these three possibilities we have, which are still compatible with the assumption of isotropy and homogeneity. And as I said, I put this explicit scale here, and this allows us to still set the scale factor to 1 today. because in the previous lecture it was mentioned that once you have spatial curvature, you cannot do that anymore, but you still can if you put that scale explicitly here. Then you can do a rescaling of the radius and this scale to, without loss of generality, we can say that today A is 1. Okay. Then still we will mostly be concerned with the flat case in this lecture. And what is important is that, and we have already heard it, that R itself is not physical. It's instead it's a co-moving scale. So what does co-moving mean? It means think about a balloon you blow up, and you can put coordinates on that balloon, and you would call them co-moving coordinates. Their physical distance increases as you blow the balloon up, but these coordinates are moving with the expansion. So this really is the meaning of these co-moving coordinates. Oh, that is, it's my way of writing an R. It's not gamma. Gamma would be like that. So just to, yeah, I know my handwriting can be a little bit tricky, so it's good we clarify these things. Okay, so the physical coordinate instead is the one that scales with the scale factor. Okay. And it of course changes in proportion to the scale factor. And then it's also very convenient for us to introduce conformal time. So conformal time is defined as the integral dt over A. And in that case, it's easy to see that then the scale factor, as we have seen before, pulls out. And we introduced the convention that a derivative with respect to eta is a prime. And sometimes I will switch between those things. So sometimes it's a dot, then it's derivative to FRW time, and prime is going to be a derivative with respect to conformal time. One more thing, I haven't talked about the conventions yet. So we will work in mostly plus metric conventions, and we will set H bar and C to 1, and I will use the reduced Planck mass occasionally. Okay. Yeah, back to the conformal coordinates. I mean, the nice thing then is that what we have in the flat case is that A squared pulls out, and we get A squared times Minkowski. And this makes it very convenient for studying the propagation of light, because then light moves along straight lines or angles of 45 degrees in a diagram of time, conformal time and space, conformal space. So we have that ds squared equals 0. If we look at a radial movement of light, it's going to correspond to dr by d eta equals plus minus 1. Okay. But then there's also the curved, the case with spatial curvature. And here it's useful to introduce a new radial coordinate, which takes care of this factor, so to say, because this really is no longer the proper radius. It's more like the proper surface scale. So we introduce this chi, which we define in the following way. D chi is then dr divided by square root 1 minus k r squared divided by r0 squared. Yes. And then the propagation of light is going to be along lines of corresponds to straight lines in this chi coordinate. Okay, very good. Where's the eraser? Sorry, the sponge for. It's one of these, right? Yeah. Okay, sorry. Okay. So as we are going to talk a lot about the Hubble tension and the expansion of space and the Hubble rate, let's start with the concept of expansion. And as you all know, the expansion is quantified in cosmology through the Hubble parameter, A dot over A. And of course, the observation tells us that the universe expands, so H is positive. Yeah.
Usually we don't see this R0 in
Yeah. I just like to keep it there because it allows us to keep track of the curvature scale easier. So you can set it to 1, but then you lose the freedom to make this choice. So it's a, yeah. I mean, depends a little bit on your taste of how you want to perform the calculation, I think. Yeah, yeah.
Will not that scale go inside?
Yeah, exactly. I'm going to write it down later. It goes inside there. Yes, absolutely. Okay, very good. Yes, and as you know, Hubble rate today we call H naught. Very good. And then what we will need a lot is the conformal Hubble rate, which is A primed over A. So it's the derivative taken with respect to conformal time. And if you then use this transformation, you find that it's A times H. So you just use that d eta is A times d eta is dt. Okay. Then another, as we have already heard, another important concept related to expansion is, of course, redshift. So you look at light propagation, and what you find is that if you start at some time eta, and with some light source, with a certain wavelength, lambda, as time evolves and space expands, these wavelengths are being stretched. So at a later time, let's say today, so the subscript 0 always stands for today, you are left with a larger wavelength, and we quantify that in terms of the redshift. And the redshift is very important for cosmology because it's a very convenient time variable. So we use it instead of time very often. And also because it's closer to observables. And here you also see why this eta variable is so useful in cosmology, because, so imagine now you have light propagation. So this is a space direction, conformal, using a conformal coordinate. And this is conformal time. So we have seen that light then moves on straight lines of 45-degree angles. So if we are here today and the light source is here, so this is the observer and this is the source, then you are going to see that the light moves on a straight line. But if you think about the wave, and this is the trajectory of one peak in the wave, the neighboring peak moves on a slightly offset direction, but still on a straight line. So that distance here, delta eta, is preserved throughout the propagation of light, which means that the wavelength here is just delta eta, but this is the physical length scale. So in order to convert a conformal scale into a physical scale, well, what do we need to do? We have to multiply it by the scale factor, A0. And the same here. So this would be lambda at the source, lambda 1, or just lambda, and it's delta eta times A at that time when the source was emitted. Now you plug this into this formula here, and you find that you get A0 minus A divided by A. And since A0 is 1, we just get this, which is the formula for the redshift. So you see, once we work in conformal time, light propagation is just very simple, and we can infer these relations rather easily. And this is going to be important because in this lecture I'm going to talk rather a lot about distances in cosmology, because measuring the Hubble parameter in cosmology requires measuring distances. So that's the reason. Okay. Then, yeah, let's have a first very naive look at distances at this stage. I mean, this we will do in more detail tomorrow. So to do that, we expand the scale factor around today. Just Taylor expanded. So we say the scale factor is that A dot T minus T0 plus higher order terms. And then we can identify the Hubble parameter by pulling out a factor of A, but this is 1 because it's today. So we can write it as 1 plus T minus T0 times H naught. Okay. And now we can introduce a physical distance scale, because this is physical time. So this would be the naive distance scale we would come up with, which is T0 minus T. Remember, the speed of light I set to 1. Very good. And then what we get, we can calculate the redshift, which we have seen as 1 over A minus 1. And if we plug in this result, what we get is 1 minus dH naught. So it's minus because d is T naught minus T. So you get a sign here, minus 1. And since we are working now in the limit of a small expansion and small redshift, this is small, and we can just write it as 1 minus dH0 minus 1, which is dH0. So what we found is a relation between redshift, distance, and H0. So this is the famous distance redshift relation. But we will see this is only meaningful if you talk about relatively short distances or small values of the redshift, and we will generalize this formula in different ways tomorrow. But this, in principle, this is why I said measuring H0 requires measuring distances, because here you see if there is a source, we know the redshift of the source, so by how much the wavelengths of these photons have stretched, and we know the distance, then we can infer the Hubble parameter. So this is a very, very basic but important observation in cosmology. And what one finds is that the Hubble parameter, well, is a number of order of 70 kilometer per second per megaparsec, where this 70 now is just a ballpark number. We are going to talk about specific measurements in more detail and what they give. So CMB measurements, supernova measurements, and yeah. Yes. The scale does not appear anywhere in this calculation. Yeah. This calculation, I mean, at this stage, it's right. At this level, it doesn't appear, but it would at higher orders. And actually, there is a problem on the problem sheet where you are going to work out the distance redshift relation for a certain distance measure in the presence of this curvature term. And that should exactly answer your question, how curvature shows up in these scales. Yes, very good. Okay, yeah, that's what I wanted to say initially about the geometry of an FRW space-time, how it relates to redshift, and we had a first encounter with the Hubble parameter and how, in principle, one would measure it. So let's move on to the dynamics. And well, as you know, I mean, we are working in the framework of general relativity. So at a somewhat more fundamental level, we start with the Einstein-Hilbert action. Where R is the Ricci scalar, and I include a constant in this action, which is something you can do, which is compatible with the general covariance of that theory. So it's still invariant under general coordinate transformations, and I also include matter, and matter at this stage could be anything. And then, as you know, we obtain the Einstein equations by varying this metric with respect to G. And what we get is the Einstein tensor, which is a function of the metric plus the cosmological constant term equals 8 pi G, and the energy momentum tensor, where the energy momentum tensor you can infer by doing the variation is -2 divided by root minus G partial minus square root minus G times the meta-Lagrangian. Okay, so this, I write this down because already at this stage you see that the cosmological constant, you can, you have a freedom here to put it on the left-hand side of the Einstein equation or to absorb it into the energy momentum tensor. And what we will do here, we will absorb lambda in T mu nu, and we can always achieve this in terms of a simple shift. So T mu nu goes to T mu nu plus, now we just need to take care of the 8 pi g, and then we get this g mu nu. Okay, so then as you have already seen in the last lecture, in cosmology we make a very simple ansatz at background level at least, and we ignore inhomogeneities of the energy momentum tensor as an ideal fluid. So G mu nu is just a diagonal matrix of a background energy density. So typically background quantities I will denote with a bar and then the pressure components on the diagonal. So this is the expression for perfect fluid in its rest frame. And then we can use Bianchi's identity. So we act with a covariant derivative on Einstein's equations. Then you know that Bianchi tells us that this is vanishing. And then we get the conservation of the energy momentum tensor, which is this equation. And in problem 1, you are going to work out that this implies the conservation equation, rho dot. So you remember dot were derivatives with respect to FRW time plus 3 times A dot over A times rho plus the pressure. So that's the energy momentum conservation. And this equation we can integrate up in rather general terms. And I realized that you have probably all seen that, but since in this lecture we are going to talk quite a lot about fluids and describe unknown physics in terms of fluid physics, ideal fluids, I think it's important to set or to define these basics. But of course, what you see on the level of this equation is that it's not a closed form equation. You have two functions, rho and p, and a priori, they are independent. So we need to do something to close this equation. And this is where the equation of state parameter comes in. And it's a relation between the pressure and rho. And in general, it can be a function of redshift. So this is still the most general thing you can do. And then you can integrate this equation up. And what you find is that rho at a certain value of the scale factor. So I should say I'm going to use the scale factor and redshift as interchangeable time variables throughout this lecture. So sometimes it's more convenient to use the scale factor, but you can always convert, of course. So what you get is that this is some reference density at a certain redshift. So for example, today, and you get this integral expression, ln A 0 at the reference point to ln A d ln A, oops, 1 plus W of A twiddle. Okay. So first of all, if you evaluate the right-hand side at A0, you see this becomes 0, and you just get rho 0. But at any different time, you need to integrate all the time dependence or the scale factor dependence of the equation of state parameter. And you can easily check that this is the right expression if you substitute it back in here. So this can be written as 1 plus W times rho. This gives you this structure. Then if you plug in this formula, the time derivative brings down this factor together with a factor of 3, which cancels then this factor. Okay, and the most important case is, of course, the case where W is a constant. And in that case, we get a very, very simple scaling where rho is proportional to a to the power minus 3, 1 plus W, which you can easily see by assuming that W is constant. You can pull it out, you can do this integral on an elementary level, and then you get exactly that scaling. And for example, and you have heard that in the previous lecture, if W is a third, you get a scaling which is 1 over a to the power 4. So that would be the case of radiation. Okay. But having this general fluid ansatz also allows us to evaluate Einstein's equations further, and you have seen the Friedmann equations before, but just for completeness, let me write them down. And we have now also the curvature term, and there the scale is still there. A dot divided by A is minus 4 pi G divided by 3 rho plus 3 times P. And now at this stage, you might wonder, we have now three equations for rho, P, and A. So you wonder why aren't, if these are three independent equations, why did we need to specify the equation of state parameter? Well, the reason is these are not entirely independent equations. So from these two, you can derive this one. Okay. But this is all the math we essentially need to describe the background evolution of the lambda CDM model. So finally, and you're going to do that in the exercises, you can derive the solution of the Friedmann equation for a single fluid with general equation of state W. And what you are going to find is that you get this solution if you do it in FRW time, 2/3 1 over 1 plus W, but you get another solution in, I mean, it's physically the same, of course, but another form of the solution in conformal time, which is this. And both things are very useful to have, and we will use them quite often. Yes, and you can also from this derive the conformal Hubble parameter, which is going to be 2 divided by 3, 1 plus 3W, 1 over eta. So this is something important to keep in mind. The Hubble parameter, the conformal Hubble parameter scales like 1 over eta, the usual Hubble parameter like 1 over t. So as we go to earlier times in the universe, Hubble becomes bigger. Okay, then we are ready to write down the background model. Yeah. Okay, so I should say these formulas hold if W is larger than a minus a third. So it's true, and we are going to talk about it. Once you are in a de Sitter or quasi de Sitter, the relation changes, and you have to be more careful. Yeah. And then you need to introduce an offset in eta. Then you can still keep it positive, or you go to negative values. Yeah, that's right. Good point. So, okay, the background model. here we say that the energy budget of our universe consists of 4 contributions. There's a radiation, a matter, and a cosmological constant, or let's start with curvature first, curvature contribution and a cosmological constant contribution. And radiation, this, as you know, is relativistic matter. So in a particular cosmology, and we are mostly interested in not too early times. So we assume that we are already after electrons have become non-relativistic and have annihilated. So radiation in our case is mostly neutrinos and photons. And then we know we have an equation of state of 1/3. And that is something you can derive also from the equilibrium distributions. But as we have seen, this corresponds to a radiation that scales as 1/8⁴. So it scales like 1 over volume times 1 over A, where this volume scaling is just because you dilute the number density of particles, and this is due to the redshift. Yes, and as I said, we are after E plus E minus going to gammas. Otherwise, you have to be a little, well, you have to take into account that the temperature changes in this process, but after that, you can also just write down what rho is in terms of a temperature. You can say it's the effective number of relativistic degrees of freedom. We are going to define more carefully what that is later on in the lecture. It becomes important for these dark radiation models. Pi squared over 30 times the temperature to the power 4. And now if the number of relativistic degrees of freedom is constant, it isn't constant all the time, and we'll be looking quite a lot at cases where it's not constant. But for now, we assume it's constant. And then you find that A scales like 1 over T. You have seen that today before. Okay. So this is the radiation case, but then there's also the matter contribution. And here the equation of state is 0. So matter then scales just with the volume. And oh yeah, I should say here in the radiation case, I wanted to add that that's quite important for us. If radiation dominates the energy budget, then we are in what is called radiation domination. And then what you get for the scale factor is that it scales as root T, or more importantly, in conformal time, it's just linear in eta. So that's something important to remember. We need that all the time. And okay, in the matter case, so if rho matter dominates the energy budget, then you get that A is proportional to T to the power 3/2, or to eta squared in conformal time. Okay. Actually, I'm not sure. Can you see what I'm writing down here when you're on the other side of the room? It probably gets a little bit hard, right? In any case, there are the notes. Okay, and then finally there is the curvature contribution, which I just write down. I mean, it's really a geometry effect, so there it doesn't make too much sense to talk about an equation of state, but you could see it. You could formally describe it with an equation of state, which is -1/3. And then there is the cosmological constant. And this is what we call dark energy. At least in the lambda CDM model, dark energy is just a cosmological constant. And then the equation of state of dark energy is -1, because then this equation tells us immediately that rho is constant, which we need. And rho lambda would be lambda divided by 8 pi g Newton. And it's a constant. Okay. I should say that this is when people talk about the lambda CDM model, that's what they mean. Dark energy is a cosmological constant. It corresponds to an equation of state of -1. But people go beyond that quite a lot nowadays. So it's maybe also useful to write down how you would generalize that easily. So you could say that dark energy is only close to -1. And then people parameterize that in terms of a derivative, a non-vanishing derivative at 0, which is called WA typically. And there will be an exercise where you play with this a little bit. And of course, in this dark energy case, what we get if dark energy dominates, so for rho lambda, larger rho total, we get a quasi de Sitter. So in particular, we get that A double dot is larger than 0, which means we have accelerated expansion. Okay. Let me go all the way there. And now we have understood, at least at a very phenomenological level, what the different contributions to the energy budget are in principle and how they evolve with time or the scale factor. And now again, we derive the dimensionless fractions of these different components, rho I, which is just divided by the critical density as you have seen before today. So where the critical density simply is 3h naught squared divided by 8 pi g. And we have seen the critical density, you compare it with the energy density you put in the Friedmann equation, and if they are equal, you are in the flat case, and if they are not equal, you are either in the open or closed universe case. But having this definition allows us to rewrite the first Friedmann equation very easily. So you just take the first Friedmann equation and you divide it by rho critical, and then what you get is a nice and very convenient parametrization of the expansion history of the universe. So what you do is you use that rho total is again the sum of these three contributions, but now you divide by rho critical, so you get all these omegas. And what it looks like is that the Hubble parameter as a function of redshift is h0 squared times the sum of all those omegas. So let's start with omega lambda, the cosmological constant contribution. There we have seen it's constant, so it doesn't come with any time dependence. Then there is the matter part. There we have seen it scales with the scale factor as 1 over a cubed. If we write that as a redshift, it's 1 plus z to the power 3. So you remember that 1 over A is 1 plus Z. Then there's the curvature contribution, which would be 1 plus Z squared, and there's radiation. Put it here. 1 plus Z to the power 4. Okay. And then evaluating this equation today, so this becomes H naught, then you can divide it out. And what you get, and all these factors evaluate to 1, so you get a constraint on the omegas. So you see that the sum of them all has to be 1. So they are not all independent. That's something very important to keep in mind. Okay, and this now allows us to learn already at this simple stage. I mean, we haven't done anything complicated, you would probably agree. Just looked at the Virmani equation, made a simple ansatz for the fluid, solved it for these kind of simple ingredients, matter, radiation, curvature, cosmological constant. Oh, yes, very good. Otherwise we are in trouble, I guess. So, okay, then we can already at this level talk about concordance, because sometimes the lambda CDM model is called the concordance model of cosmology, and I wanted to have that rather early in the lecture, just to back up what I said in the beginning, why we are so proud about that model. So what you can do, you can look at a plot where you have on the y-axis omega lambda, on the x-axis you have omega matter, and then, something should be said. Omega radiation, it scales most aggressively with the scale factor. So omega radiation at late times is, it scales down very quickly. It dominates at early times, but it's negligible at late times. So omega r is order 10 to the minus 4. So we can forget about omega r. And then we see there is a relation between, that actually should be lambda, sorry, between omega lambda, omega m, and omega curvature. And if the sum of omega lambda and omega m is 1, then curvature has to be approximately 0. Yeah, so omega m plus omega lambda being 1 implies that omega curvature, for all intents and purposes, is 0. So we can already write down in this plot this line, which corresponds to a flat universe. Okay. And now I'm just going to tell you what 3 different measurements, how they constrain this plot. I'm not yet going to explain how these measurements work. That we are going to do tomorrow in more detail. But just as an initial idea of why this model is so spectacular. So there's something we call the Baryon Acoustic Oscillations, BAO, and they give you a constraint which looks a little bit like that. I mean, I'm not going to be super precise here, so let me use a different color for the other ones. So BAO has to do with the large-scale structure of the universe and how certain features from the early universe are imprinted in that large-scale structure, and we can measure that and constrain omega lambda and omega m, but the details don't matter now. Then there are supernovae, which give us a different constraint, which is tilted at a different angle. Again, we will learn later how these measurements work. And then there is most famously, and you're going to hear a lot about it, the CMB measurement. And the CMB measurement. So first of all, nothing fancy is happening here. You see, you get these very elongated contours, and well, they have to overlap somewhere, right? So that is maybe not so exciting, and you would say, okay, the true universe lives somewhere in that region. But now there's a third independent measurement, which is the CMB measurement. And the CMB measurement, I mean, it could have been here in the plot, and then you had been in trouble, and you wouldn't call it the concordance model of cosmology. But what happened is it sits here. So not only do you see that all three contours overlap roughly in the same point, you also see that it corresponds to flatness. Yeah. 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 That has to do with how we do the measurements with distances. So, and how these distances scale with these components. And it's very sensitive to where the redshift of that distance measurement is. So we will see it has to do with the fact that the CMB essentially is a measurement taken at relatively early times in the universe, redshift set of the order 1,100, and these measurements are taken much later in the universe, and that changes the dependence on these, the dependence of the observables on these quantities. We are going to see why, but at this stage, yeah, I just want you to appreciate that. So when people talk about the concordance model, this is one of the reasons why at background level you can already see it's non-trivial. So okay, and we are also going to learn. I mean, there are these elongated contours, right? So there is a degeneracy between omega m and omega lambda. And this has to do with the freedom in curvature. So these are called geometric degeneracies. And there's going to be an exercise where you actually derive the slope of that supernova contour, I think. Degeneracy. And we are compatible with flatness. And you might have heard in last week's lecture on inflation that inflation is one of the ways we try to make sense of that observation. So compatible with flatness. So omega k, what we know from observations, it's somewhat smaller than 0.01. And for that reason, we mostly set it to 0 exactly. But of course, once you go beyond lambda CDM and you're interested in new physics and so on, you might reconsider that choice. But at this stage, you set it to 0. And yeah, this is what we mean by the lambda CM models, and the values. I've stated them already in the beginning, is that omega lambda is 70%, omega matter is 30%, and 5% of that is baryons, and 25% is dark matter. But these are very approximate numbers. I mean approximate plus minus 1-2%, because it depends on what data set you use to constrain these numbers and so on. But these are the numbers you typically remember, just to have something to play with. And of course, as I said before, the main mystery at background level is already what dark matter and dark energy actually is. I mean, we say here it's a cosmological constant, but I will later in the lecture, tomorrow or the day after, I will argue that this interpretation is in itself problematic. Okay, so then I should speed up a little bit. So we can, now that we have kind of established these quantities, we can also write down the history of the universe. And that is a very important plot you should keep in mind. So if we look at the different energy components in the universe as a function of time at background level, then we see that there are radiation. Initially, we start out with radiation domination because, as I said, it scales most aggressively with the scale factor. So we have something that, so this is a log-log plot, something that goes down like a straight line. Then there is matter, which scales only with redshift to the power 3. So that comes in at a slightly smaller slope. So this would look like this. So you have some time where both lines overlap, and this is what we call matter radiation equality. So as a ballpark number, it's around a redshift of 3,400. Then a little later, there's what the CMB is formed. This is the snapshot of the early universe, right? It's at redshift 1,100 roughly. So just to give you an idea of the numbers involved. And then there's also the cosmological constant, which is just a constant, which is highly subdominant at early time. So if you do early time physics, and we will talk about CMB physics and so on, we never include it because it's very suppressed, but it's also very stubborn, so it catches up eventually. And then you end up with this dark energy domination today, and this happens at a redshift of roughly 0.3. So there are these 3 epochs. That's important to remember. There is the radiation epoch. There's the matter epoch. And there is the dark energy epoch. This is where we are today. And, yeah, and we would be at Z equals 0. So, yeah, and then CMB physics happens somewhere here. And as I said before, these measurements are taken at much later times. And as you will see, this also relates to these shapes. Okay, so this is the history of our universe. And yeah, let's keep it like that. And then I have another 20 minutes or so to do a little bit of perturbation theory. So this was very simple kind of background evolution of the universe and the first taste of the lambda CDM model. But its real power and strength, it plays out at perturbation level, because the observables we have are observables that relate to perturbations in the early universe. As you know, these perturbations are seeded by perturbations in the inflaton at early times, but then they evolve throughout the cosmic evolution. And then we measure the CMB that decouples here. And what we measure are essentially the perturbations that have started way earlier and propagated up to that point. And then they keep on propagating, leading to structure formation and so on. And then we take another snapshot, which we call BAO and so on. So that's the philosophy. So I'm not going to give a lecture on perturbation theory in cosmology, but I still need to cover some concepts at a basic level to make this whole lecture somewhat self-contained. So I call it, this is chapter 2, and I call it Inhomogeneous Universe. And the idea here is we started out with a perfect fluid, homogeneous and isotropic, and now we perturb that perfect fluid. But when we perturb the fluid, as you know, it feeds back into the Einstein equations. It's also going to perturb the metric. So we cannot perturb the fluid without perturbing the metric. And I'm going to write down an ansatz of how we are going to do that. So now we are working in the flat case. I want to keep things as simple as possible. In principle, you can do perturbation theory also in the presence of curvature. It just makes things more complicated in terms of the notation. So the background value here, so this is what multiplies the d eta squared. We work in conformal time. And the background value would have been the 1. But now we introduce a small perturbation, psi. So psi is assumed to be small. And importantly, it depends on time and space. So we allow for space-time dependent perturbations of the background metric. And one more thing, we are also right now only interested in scalar perturbations. So objects that transform as Lorentz scalars under Lorentz boosts. So that is also important. I mean, there are vector modes, there are tensor modes. So if you're interested in, say, gravitational waves and how they influence the CMB, you would need to include tensor modes. But I want to keep it simple and focus on scalar modes, which are enough to capture the physics of a perturbed ideal fluid. Okay, dxi. And now I use Cartesian coordinates instead of radial coordinates. And the scale factor multiplies everything, of course. Okay, so you see there are two independent functions, psi and phi. And what I claim at this stage is that this is the most general perturbation at scalar level you can write down. But there's going to be a problem on the problem sheets where you argue that this is actually the most general thing you can write down. To see that, you need to use the fact that we are in a theory that comes with redundancies. There are diffeomorphisms, so small coordinate transformations, and you can use them to bring the metric into this form. But for now, you just need to believe me and convince yourself in the exercises. So, okay, this is what we do on the level of the metric, but then we also go to the energy momentum tensor. And there you have seen at background level, this was just, the 0,0 component was just minus rho. So now it's minus rho plus some delta rho, where delta rho again depends on eta and x. So I'm going to drop this argument. Whenever I write delta, it's understood that they have a more complicated dependence, whereas the background quantities, of course, only depend on eta. And we also introduce here the density contrast, which is a very useful quantity, which is defined as the ratio between these two quantities, delta rho and rho bar, the background value. Then there's the off-diagonal element. At background level, you have seen it's 0, so it doesn't come with a background term. So we write it like that. Yeah, we are only interested in scalar modes. So this is a partial I, so partial spatial derivative of a perturbation I call V, because it relates to the velocity of the fluid. So before, on background level, we could always go in the rest frame of the fluid, so the velocity is vanishing. But at perturbation level, we have a velocity field, because if you go to different places in the fluid, you are going to see it move with different velocities in different directions. And then finally, there is the IJ part, which before was the pressure, right, at background level. So that term is still there. But now we put a pressure perturbation. It was also diagonal. But now in general, there's also, you can also have a traceless component, pi ij, which is called the anisotropic stress. So, okay, let me write down a few things. So this is the bulk velocity. Bulk velocity V. And it's also convenient for later usage to define the velocity divergence. Which is theta equals partial I VI, where VI then is this we would call the vector. Okay. Then this is the bulk velocity. And here we have the pressure perturbation, which is of course important, but also the anisotropic stress. So pi ij is anisotropic stress. But the nice thing is that for most parts we can ignore that. The only source of anisotropic stress in the early universe are neutrinos. So if you run a realistic Boltzmann simulation of the early universe, and you're, by the way, you're going to do that at some point this week, then this is being included in the code. But to get a good feeling of what's going on, just because neutrinos, we can neglect the anisotropic stress from neutrinos. So we set it to 0 for simplicity, knowing that it doesn't, I mean, for these qualitative statements doesn't make a big difference. And then there's, of course, the pressure perturbation. So let me summarize. We have metric perturbations, psi and phi. By the way, this is called the Newtonian gauge. There are different gauges. So I guess last week which gauge did you use last week mostly to do inflationary perturbations? Do you remember? Spatially flat gauge. Yes, that's, and there's you can work out the relation between Newtonian gauge and spatially flat gauge. But there are many gauges. Also, this is a very common gauge if you do perturbation theory. So you're already later in cosmology, because then you can relate these quantities with the non-relativistic quantities you are used to, like the Newtonian potential, which plays the role of phi then. But then there are also other gauges. And I think in the exercise you work out the synchronous gauge, which is the gauge which is used in Boltzmann codes. But in any case, there are these different choices. Okay, then we introduced a perturbation of the energy density. We introduced a velocity perturbation, or the divergence of it. So mostly, I think we will write down theta, and then there is a pressure perturbation. Okay, fine. And as we did on background level, there's also on perturbation level a composition of these different quantities. So delta rho is the sum of I, delta rho I, and delta P is the sum of I, delta Pi, and here for convention you have always this factor of rho plus P, which has been scaled out of this quantity, so you put it here too. So you have that this is the sum of I rho plus Pi, delta Pi, and the I's are all the different things we have in the cosmic fluid that behave differently. So we have photons, we have neutrinos, we have cold dark matter, we have baryons, and so on. Well, these are actually on the level of the simplest perturbation theory. These are the things you would be looking at. Okay, but this is just for completeness. Don't worry too much about this detail, because what we are going to do now is look at the simplest case where we only have one component with a fixed equation of state, and just try to understand a few general things, how perturbations in an ideal fluid behave. And what we will see is that in general they lead to oscillatory perturbations. Okay, so what we do now, we assume single fluid with constant equation of state. Well, for now, not even that. So we have a single fluid with some equation of state. But then, very much like you remember on background level, we needed this to close the equations. Otherwise, we couldn't solve them. We needed the equation of state parameter. And something similar happens at perturbation level. There we need to impose a condition between the pressure perturbation and the energy density perturbations. And I will motivate that later a little bit more, but we say we have so-called adiabatic perturbations. And then these are nice because then this relation follows from the background. So delta P divided by delta rho is just d background P divided by the background rho. And that we can rewrite a little bit. We can say this is dP by dt times d rho by dt to the power minus 1. And then we can just use what we know about the background and how it depends on the equation of state and so on. So actually, we instead of t, let's use eta. So we can easily calculate that. So P we know is d by d eta. P is W of A times rho. And d rho by d eta, there we can just use the energy conservation equation, which is 3 Hubble rho bar plus P. So this is just the background energy conservation. So now the derivative can act on W because the equation of state can be time dependent. So we get a term which is, and this is also a function of eta. I mean, it doesn't matter whether I write it as scale factor or eta, divided by minus 3h 1 plus W. And there's another term where the eta acts on rho dot, but then this was also just rho dot, just rewritten. So this is just plus W. Okay, and this is an important quantity in perturbation theory. This is what we call the sound speed, and you will see why we call it the sound speed. This is the adiabatic sound speed. Yeah. I mean, so you already see here the components we consider: photons 1/3, neutrinos 1/3, cold dark matter 0, baryons, equation of state 0. I will shortly mention about the cosmological constant, because that is particular with respect to perturbation theory. Sort of perturbation theory doesn't apply to a cosmological constant if you want to, or trivially only. Okay, so do I get five more minutes? Or okay, I try to be quick. So now we go to momentum space. So a quantity like that we write as in momentum space via the Fourier transform. Now I just need to get the convention right. Okay, I don't have a factor of pi here. BIKX delta eta x, and and partial derivatives, of course, go to I times factors of ki. It's just a consequence of the time derivative, and I define k as the norm of the spatial momentum vector ki. So in other words, I go from position space, three-dimensional position space, to three-dimensional momentum space, but I leave the time variable untouched. This is what we typically do. And yeah, with this convention also this velocity divergence is just minus k squared. So yeah, this all requires a little bit of notation and so on. But once we have set it up, it's actually fairly simple. So let me finally write down two equations. And these are the perturbed fluid equations you get once you define things in that way. So what we get is, just very quickly. So we perturb the energy conservation equation. I'm not going to do that in detail, of course, but this is what you should, I mean, what in principle you do. You take the covariant conservation equation and you look at linear perturbations when you substitute in these Ansätze, and what you get are two equations. There is the one corresponding to this index being 0. This is the continuity equation. So you get that delta primed is minus 1 plus W, theta minus 3 phi primed. That's the gravitational potential. Delta, so that's the continuity equation. And if you look at spatial components, we get the Euler equation. So the continuity equation tells you how the energy density contrast changes as a function of time, as energy flows out of a given volume. And the Euler equation tells you how this flow changes with time. And it's given by, on the right-hand side, by some force terms. One is the pressure term, which is this one, 1 plus W, just need to, and a gravitational term. So these are the two equations controlling the dynamics of fluid perturbations. So this is the continuity equation. This is the Euler equation. And so structurally what you have here is, this is the fluid flow. So if you have a given volume and fluid flows out of it, you are going to lower the density contrast. Then you have the gravitational potential here, which is kind of a local curvature effect. And also this term, it's proportional to Hubble, is an expansion effect, which you only have because space is expanding. In a non-expanding Euclidean space, you would only have this term. And then there's the Euler equation. There's again something which has to do with the expansion and to a pressure term and a gravitational term, which would be the gravitational force acting on this fluid. And as you see, this is not a closed set of equations because there is, we have delta, we have theta, but we also have a dependence on the gravitational potentials. And so we also need to look at the perturbed Einstein equation to close this system. But already at that level, we will see tomorrow that we can learn quite a lot about how these fluids behave, why we call this a sound speed, and then we will look at the radiation case and the matter case and also the case of a cosmological constant to get a feeling for how these different components in the lambda CDM model, how their perturbations behave. And that already gives us an idea of what the CMB is about and what large-scale structure is about. I mean, that's at least going to be the aim for tomorrow. And then we are equipped to properly learn about the Hubble and S8 tension and to see how they are derived. Okay, that's it. Thank you.
Any questions? Okay, we have many hands.
So, sorry?
how can we change these equations to incorporate that quintessence equation of state?
Quintessential equation of state?
With omega 1 less than 1 minus 1 by 3.
Oh, yeah. Okay. I mean, then you are talking about dark energy perturbations. So first of all, for early universe cosmology, you wouldn't care about that. So it becomes important later on. And then indeed, you do perturbation theory for these quantities. But then you have to be careful because you see we have these factors of 1 plus W floating around here. So set this to -1 and you are in trouble. I mean, you divide by 1 plus W. So in that case, you need an adapted perturbation theory which allows you which gets rid of these singularities, which are only artifacts of how we set up perturbation theory. So in principle, that can be done, but it's not part of the lambda CDM model. It's just a cosmological constant, and we will see that doesn't support its own perturbations. Okay. Yeah. Yeah. No, go ahead. Yeah. Peculiar velocity. No, no, that is, yeah, I haven't thought long about it, but I think you should think about it as distinct things. I mean, this is really looking at perturbations in an ideal fluid. At late times, I mean, you have nonlinear structure formation, and that's a different realm, so to say. Yeah. Tidal, yeah. Yeah. Good question. I think tidal forces with wouldn't be part of that description. So my guess is they come from somewhere else, but yeah, not entirely sure. Yeah, I think you were first.
When you calculated the perturbation of the stress tensor, the stress tensor itself has some metric factors, right? There's a pressure times G mu nu in the stress tensor. Where is the variation of the G mu nu in the stress tensor?
I didn't. Are you asking about the perturbation theory?
Yeah.
And which part? Sorry.
So I think I'm not very sure, but in the TIJ you'll also have. I mean, in general, T mu nu has a G mu nu times P, right? There's a P times G mu nu in the T.
You are asking about additional components here. You could look at.
Yeah, so when we write down the stress tensor, it has a u mu nu and then a G mu nu, right? For an ideal fluid.
The U of the general fluid, the four velocity perturbation.
There's a four velocity u mu u nu. There's one term, and there's a G mu nu term.
Oh yes,
metric
exactly.
Term. But then for this, the change of the stress tensor, we also should put in the change of the metric, right?
Yeah. But okay, let me think how it happens here. I mean, one should say these depend. These decompositions also depend on the ansatz for the metric perturbations. So this is what you would do in. This is what you find in Newtonian gauge. I'm pretty certain. So you are asking why isn't there a psi and a phi showing up in these decompositions?
Let's take the TIJ, the space part.
Yeah. So now I understand. we take components up and downstairs for that reason, right? I mean, this is why we do that conveniently, because then, so if you pull that index down, you get exactly that dependence on the metric perturbation. But if you take these up and down mixed indices, that you do for exactly that reason, then it turns out that they cancel out. Yeah, which is kind of obvious to see, because then the metric becomes a Kronecker delta, right? So this is why they are not showing up there. Okay, very good. Oh, yeah, very good question. We are going to talk about, I wanted to do it today, but I'm slow. I wanted to talk about initial conditions. I'm going to talk about it tomorrow. And you have learned them last week. I mean, at least one possibility for initial conditions. So they are set up for us by inflation. And so what we will consider are so-called adiabatic initial conditions. And I'm going to explain what they are. But of course, they are going to define the initial conditions for these equations. Yeah.
Questions? So if not, let us thank Professor Florian